So we've got a graph here showing how the force due to friction varies with the applied force as the applied force is increased. So let me just step you through this graph to show you what's going on in each stage. And so initially we're down here, so we've got zero applied force, and that means we've got zero friction. And so the situation is something like this. I better draw a surface, actually. This must be sitting on something. And so you've got some surface like so. So you might have some steel block sitting on, might be another block of steel. You've got steel-steel interface. I might just give this a bit of a colour. So something like that. A bit garish, but anyway, that's okay. And so that normal force must be equal to the weight of the block, because you need to have static equilibrium. Let's try and bring that to the front if I can. Okay, so that's that first point. We don't have any force applied. Then let's move around this graph. So maybe we come up to here somewhere. So we've got some kind of applied load now. And I might have to move everything across a little bit. Excuse me. And so we started down here, now we're moved up to this point here. So we've got some applied load P, so let's just copy all of this. Not that, this. And now what's going on is we've got an applied load P, ruler, excuse me, so we've got some P, and it's not too big yet, so just a little load, like so, say. Then, to balance that, we must have a frictional force. Now, often you'll see these, I've drawn these, but I don't think I've explained it yet. I'm not going to be too careful about where I draw it. Just need to be able to see it. Oh, but I do need to be careful about how long I make it. And so that frictional force is going to be in the opposite direction, because it's going to be balancing that force. And it must have the same magnitude. Let's just do it as a normal arrow, actually. Sometimes you draw these frictional forces with just a one-sided arrow, but we'll just do it with a normal arrow. And so you've got some frictional force F. It's not Fs yet. We use Fs when it's just about to slip. So at the moment, it's just a frictional force F, and we've got an applied force P. But the main thing is these two things must have the same magnitude. That's why this line is 45 degrees if these are the same scale. And so the value of P for this point, the magnitude of the applied load must be equal to the magnitude of the frictional resisting force. And that's why you get static equilibrium. And then, as we talked about a minute ago, we've also got some lever arm between the applied load P, let's just call that dP, for example. So we've got some lever arm between there and there, so you've got a moment. And so we must have another, and this is a couple, because these are two forces, same magnitude, opposite direction, so this is a couple. These two are also two loads, same magnitude. And what's going to happen is this is going to shift this way a little bit, so that that couple, Wn couple, produces the same moment as the Pf couple. And so you're going to have some moment. Let's just go back to see what we actually call that. So we called this, I'm just looking at our notes, we called this h, and we called this distance x. And so pH must be equal to nx, and P is equal to F, and W is equal to N, but pH must be equal to nx. N is bigger than P. The normal force is bigger than P at this stage because it's quite a small applied force, and so that X will be smaller than H. Okay, then we'd keep going up and we'd keep increasing the force, and so we might come up to here somewhere. So we're increasing the applied load. And usually your friction coefficient is less than 1, not always, but usually it's less than 1. Some rubber and stuff might be bigger than 1. But what would be happening now? Well, you'd have a similar situation. Let me just rub this out. I'm not going to show those every time, the lever arms. You can just imagine they're there. But what's happening now is we've got a much bigger force. So P has increased. Therefore, I wonder if I can delete this without deleting everything. So this frictional force must also increase. This one here was probably a little bit too long. I don't know if I can draw it really. Let me just select that and delete it. Just a wee bit too long, just to make it clear what's going on here. So it's got to be the same length as the P. And so this time the frictional force is getting a bit bigger. Still not Fs yet because it's not failed yet. So then we've got, and what else is going to happen? Well, the other thing that's going to happen is these two forces equal and opposite make a couple. They've got bigger, and so this couple is also going to have to get bigger, so that normal force is going to move a little bit further towards the front of the brick to make a moment that counteracts the moment from P and F. Then we would come up to right up to the top, and at that point it's about to slip. So it's just getting ready to slip. Let me just zoom out a fraction. So we're going to have something quite similar to this. See if that's actually copied. It has. Well done. And so what's happened now, remember your W and your N, these are never changing. It's just the weight of the block, an equal and opposite force to balance it. P is getting a bit bigger. So how can I do that? I just have to rub it out and do it again. Trying to find a shortcut. And this is probably not very accurate because P is the magnitude of this force is getting awful close to the weight of the block. So this would have to be extremely high friction. Usually the force to make it slip might be about half the weight of the block, but anyway, we're just to give you an idea, this one. So P's got a little bit bigger still, so therefore your frictional force must also get a little bit bigger, and it's about to slip. And so N will have come a little bit more this way again, because those forces are getting bigger, and what they sometimes call this is impending motion. Impending motion. And at this point, this force is now Fs because it's about to slip. And so that's your Fs. And so if you were to do Fs divided by N, that would be your friction coefficient. It's at this point here where it's just about to slip. Then what happens? Well, then it slips. And so let's just bring this across here. Just put some arrows on these to show what's going on. We'll copy this one again. And this time it's not impending motion, it's motion. So now it's actually moving this block. Once it gets to that point, and this now is going to be the kinetic friction because it's moving. So let's just tidy up all the things we need to sort out. So that's not longer, don't need to do that dashed anymore because it's actually moving. Should maybe have done it a different color. It's not a force, it's just showing that it's moving. And this would be motion. So what I'll do is just change those to black just to show that they're not applied loads. Similarly, this one, it's just showing that it's about to move. And what you can see here is you get to that static, the point of impending motion. So just before it slips, this little point here, which defines your static friction and your coefficient of static friction at this point. And then as soon as the block moves, that friction force drops a little, and it has a new name. It's called Fk. And that's the kinetic friction. And so the kinetic friction you can also calculate. So let's just put in the equations actually. And so we have the static friction is equal to Fs divided by the normal force, and the kinetic friction, sigma k, when it's moving, so when this block is moving, it's just equal to Fk divided by the normal force. Now, what's happening after that? Well, what this is kind of saying is even if you applied a bigger force and accelerated this object, this Fk will not increase. And so this will no longer be in equilibrium, so it would be accelerating. Basically, this would be accelerating off. But once you pass that point of static equilibrium, so once you reach the static friction value, the maximum frictional force you can get, once it passes that, this coefficient of kinetic friction is about this body moving, and it will no longer balance that force P. And so, in fact, we should really draw this as being a bit bigger now, because P's got a little bit bigger. So this is going to be bigger than Fk now. But Fk can't increase anymore, and in fact, it's dropped a little from the force that could be generated when it was sitting still, because basically it's riding on top of those little irregularities now. It's not keyed into them so well, it rides on top of them. And even if you kept increasing that force, you'd be accelerating the block. So let's just take it down here. It's kind of what they're showing on this graph. We take this here, stick it down here. And so if you were to take a point further along here, and even if you increase that force further, it wouldn't increase that static coefficient of friction. It wouldn't increase that kinetic frictional force, no matter how big this force got. And so this block is now moving, it's accelerating. So just to summarise, what we're saying here is we're looking at what would happen with friction if you kept increasing the force that you're applying, so the applied force. And so starting at 0, no applied force, then you've just got a weight of the block which is balanced by a normal force at the surface, so a perpendicular force at the surface. As you increase that applied load, if this remains stationary, you're going to have a balancing frictional force in the opposite direction. And that's why this line makes 45 degrees, because F must be equal to P. So this frictional force must be equal to P because you've got equilibrium, it's not moving, it's remaining static. The normal force, well, it slowly, as you start to apply a force, an applied load, it starts to move forward so that you've got a couple here between P and F. And so you need another couple between W and N to balance the moment from that. And so you keep increasing P, that normal force keeps moving forward, the force keeps increasing to balance P because it's static equilibrium, until you get to the point of impending motion, and this is the point at which you calculate your coefficient of static friction. And so you've got your friction at the point, frictional force at the point of impending motion, so Fs, and then you divide that by the normal force and you get your coefficient of static friction at this point here. If you were to keep increasing the force further, the block would start to slip and that frictional force would drop to the kinetic friction. So it would drop a little bit, and you can determine that from the coefficient of kinetic friction, this mu k, which is just equal to Fk divided by the normal force. And even if you kept increasing the force further, this block would just accelerate more quickly, if you know what I mean, accelerate at a greater acceleration. But this Fk would just remain constant, and it would just be determined by the coefficient of static friction times the normal force. You get your frictional force, so it would just remain constant. Oh, and one thing I didn't mention, the reason it's tilting down at the end here, if you kept moving for a long time, it doesn't necessarily have to be for high force. If you just kept applying this and sliding it along for a long time, you'd find that that kinetic friction would drop over time, because it would start to wear the bottom of this, it would start to smooth the bottom of that block, and so you'd start to get a lower kinetic friction. Could also increase at the end. It could also increase as this is, if it's been sliding for a long time, because you might wear off a low friction coating, or you might lose lubrication. And so it's possible that it also goes the other way, this graph, and have to go down, it could go up over time. And this is a little bit dodgy here. It doesn't have to be a force, doesn't have to be increasing force. This just could be, you could now be, actually would be better to draw this as, this. I took this out of a textbook, maybe I shouldn't have, but it would actually be better to draw that as a distance. And so if you were doing distance traveled, what you'd find is you just go straight up here because it's not moving at that point. And then it might drop away like this, and it would keep, you might be applying a constant force, and then as time goes by, that friction might drop, because it's wearing out the block. Alternatively, it might increase because you're wearing off low friction coating, or you're losing lubrication as you go along. So probably this end of the graph is better plotted as with distance that's travelled, or the magnitude of the slip rather than the magnitude of the force. Cool. Okay, next.